right, ladies and gentlemen, let's look at inverse functions a little bit more closely today, and we're kind of going to move into our new function for this unit. Always when you're thinking of your function, trail back to middle school and think of your function machine with your input following your rule and then your output. And so let's look at an example before we dive into your record sheet. If we were to put in side length and our rule was to find the area of a square, then we would be looking at area in terms of side length. And so our notation would be A of S, which we know that this is not multiply. This is showing the relationship between our two variables x and y. And so in this case, our input is the side length. And the rule that we're applying to it, our end result, is going to be the A, our area. So A of S would equal S squared. Now what we're talking about with inverse functions is we're looking at undoing the rule. So we know our result is S squared. What would it take for us to reverse that, basically? To come back through the function machine in reverse and land back where we started. So to undo that square, our operation would have to be the square root. We have to use our inverse operation, right, to undo. And so then we would end up with our S, our side length. But our inverse would be our side length in terms of our area. And we've talked about how that's not the common practice. So we would be looking at the square root of S squared, and undoing that, the square root of S squared would just be S. And so this doesn't make sense to us because that says side length in terms of area. Although it is side length in terms of area, we don't have area as our variable. Right? And so the notation that is commonly used in mathematics, not in engineering, but in mathematics, would be instead of S of A, meaning inverse, we use the notation of A inverse S. And so that to the negative 1 tells you that you're looking at the reverse. You're actually talking about your side length in terms of area. Okay, so let's look at the operation of squaring and then how we would undo that. So let's take some original numbers. I just chose some nice, neat, some negative, some positive. Got to have 0 in the mix to test the waters. And so if I want to square negative 4 times negative 4 is going to be a positive 16. Negative 3 squared is 9. Negative 2 squared is 4. Negative 1 squared is 1. 0 squared is 0. 1 squared is 1. 2 squared is 4. 3 squared is 9. And 4 squared is 16. We see a bit of a pattern continuing. We probably even know exactly what that would look like graphed from our work in Unit 3 on quadratics. So we would have a relationship between our original number and the square of that number. Now, what if I wanted to undo that relationship we just built? What if I wanted to look at my square and go back to my original? Think about the process that we went through here was squaring our number. So to then undo that, how do we undo a square? We'd have to take the square root. So let's take the square root of each of these pieces. Right? The square root of 16 is not just 4, but plus or minus 4. Right? The principal square root is always the positive, but we don't know what our original was. Was it positive or was it negative? I mean, if we weren't looking at our table, of course. But when you're taking the square root of 16, 4 times 4 makes 16, and negative 4 times negative 4 also makes 16. So when you're taking the square root, we always have to remember plus or minus, and then we'll look at the scenario of what we are talking about and see if negative is realistic or not. Okay, so the square root of 9 is plus or minus 3. The square root of 4 is plus or minus 2. The square root of 1 is plus or minus 1. The square root of 0 is still 0. And then we see our pattern continue. Okay, so when we're looking at undoing, we see our squares and then we undid them with our square root. And so those two operations, squaring and square roots, let's work on my grammar just a little bit. Squares and square roots. That's why I had 2 blanks. Oh, gracious. Too early in the morning. Squares and square roots are called inverses because they undo each other. Okay, so that's what we're talking about with inverses, is we have a process that we do. There's our function. Now let's reverse that. Let's undo all of those operations, and that would be the inverse function. So let's look at that graphically. If I wanted to look at my square in terms of the original number, let's take the ones that would fit on our grid here. I think if we start at -2, our square is 4. -1, the square is 1. The square of 0 is 0. The square of 1 is 1. And the square of 2 is 4, which that is our square function, quadratic, that gives us the shape of the nice symmetrical parabola. Okay, now if we were going to undo that, we would have our square root in terms of the square. And so let's choose some of our square roots in terms of our square. So going back to your table, the square root of 4, that will fit on our grid here. The square root of 4 was plus or minus 2. And the square root of 1 was plus or minus 1. And the square root of 0, still 0. And so that gives us a relationship between our square root and our square. Now, there are some things that we should notice. When we're looking at this, if we were to go point by point, if we were to look at, let's take this point, -2, 4, we would notice that when we're looking at the square root relationship, our graph contains the point for -2. As we look at the point -1, 1, we see that our square root relationship has the point 1, -1. And that will always be true with your functions and their inverse. You're always going to see the domain and range are interchanged. A point that was xy on your function becomes the point yx on your inverse. And so some people will call that the x and y swap. But you know how I am with math vocabulary. Domain and range are interchanged. Okay, so that's one thing that we should notice. Another thing that might pop out to you visually is it looks as though we have a reflection. And so if you dive into that a little bit further, you'll see that that reflection is across the line y equals x. Okay? And then the last thing that we want to point out is that actually, if we're looking at our square root relationship, we see this horizontal parabola. We know that this is actually not a function because we are miserably failing the vertical line test if we were to compare even just right here a vertical line passing through our graph, and we see that it fails the vertical line test. There are two y values assigned to the same x value, and for that reason we would have to restrict the domain and only look at those positive values, the principal square root, in order to get our square root function as the inverse of our quadratic. Now remember, we use this to the negative 1 to represent our inverse. So our original is f of x equals x squared. We're going to restrict our domain so that we are only looking at the principal square root. So the inverse of f is going to be the square root of x, just the positive square root of x. If we included plus or minus, we would have the top and the bottom. Okay, let's try a couple of examples. Let's look at this both graphically and algebraically. If we want to find the inverse of f of x equals x squared plus 1 graphically, what we'd want to do is to start with our original function. And if you'll think back to our work in quadratics, we know this is 1 times x minus 0 squared plus 1. We can see that our vertex hk is 0, 1. And we're opening up because our 1 is positive, our a is positive, and we have a normal width because our a is 1. So starting at 0, 1, opening up with a normal width. So from our vertex to the right 1, up 1. From our vertex to the right 2, up 4. And then mirror image that to the left to get our nice symmetrical parabola. And this would be the graph of f of x. Now remember, if we're looking for our inverse, the domain and range are interchanged. And so that means point by point by point, I can swap x and y, and those would be the points that are on the graph of my inverse. So I have the point negative 2, 5 on my function. So on my inverse, I would have the point 5, negative 2. On my function, I have the point negative 1, 2. So on my inverse, I would have the point 2, negative 1. Okay, on my function, I have the point 0, 1. So on my inverse, I would have the point 1, 0. And so on and so forth. Now, is this a function? No, because we fail the vertical line test. Right? If we were to look even just right here, we have two y values assigned to the same x value, so it's not a function, it's just a relation. So if I want to talk function, then I'm going to have to restrict my domain and just look at the principal square root. And that would be my inverse function. Okay, so algebraically, what we want to do is we want to look at f of x is equal to x squared plus 1. And we want to look at what's happened to our x and undo those operations. So what we see has happened is that x has been squared and then 1 is added to it. So we're going to have to undo those operations in reverse. We're going to subtract our 1 and then take the square root. Now, it might be easiest for you to think of this as a y equals x squared plus 1, and you're undoing those operations, so you're solving. But remember, it's the inverse, so the domain and range are interchanged. So x is equal to y squared plus 1, and then you're solving for y. So subtract 1, x minus 1 equals y squared. And to undo your square, you'll take the square root. So the square root of x minus 1 is equal to y. Or the inverse of x is the square root of x minus 1. Remember, we're not using plus or minus because we only want the principal square root so that we have a function. Otherwise, it would just be a relation. Okay, so I would love for you to pause and work with your shoulder partner on your tables to go ahead and try the second example. Find the inverse both graphically and algebraically for f of x is equal to x minus 1 squared. And when you finish and you've compared and made any necessary revisions, then go ahead and push play and come back to me and we'll check for accuracy. Okay, let's go ahead and check for accuracy. We're going to start with f of x is equal to x minus 1 squared. And so we know that is f of x equals 1 is our a, it's just invisible, times x minus 1 squared, technically plus 0. So our vertex hk, opposite of what you see in parentheses, is 1, 0. And then we know that we open up because a is positive, and it's going to have a normal width because our a is 1. So 1, 0, opening up with a normal width, so to the right 1, up 1, from your vertex to the right 2, up 4, and then mirror image that to the left. That gives you your function, f of x is equal to x minus 1 squared. Sorry about that. And so then if we want to find the inverse point for point, we can swap our domain and range. xy becomes the point yx on the inverse. So if I have the point negative 1, 4, my inverse will contain the point 4, negative 1. If my function has the point 0, 1, my inverse has the point 1, 0. If my function contains the point 1, 0, my inverse has the point 0, 1. A little overlap here. If I have the point 2, 1, then my inverse will have the point 1, 2. And my function contains the point 3, 4, so my inverse will contain the point 4, 3. So we can see the inverse relationship looks like this. Notice we do have a reflection over the line y equals x, which always happens between a function and its inverse relationship. Okay, now to solve that algebraically, we're going to say y equals x minus 1 squared is my original function. We're going to swap x and y and solve for y so that we can see the equation for our inverse. So x equals y minus 1 squared, and then we'll start undoing. To undo those operations, we have a square to remove first, so we'll take the square root of both sides. So the square root of x is equal to y minus 1. And then last step, add 1, add 1. So the square root of x plus 1 is equal to y. Now remember, we are looking at a function, and so that is going to be f inverse of x meaning the inverse of our original function, x minus 1 squared. Its inverse function is the square root of x plus 1. Only the principal square root. So really,